Hello, so we're going to look at this problem today, which is Sipser 1.31, and this is a problem that I have seen and have assigned in the times that I've taught theory of computation. And I see a lot of students miss various parts of this problem because they just go based off their intuition and don't really think about it. So I like this problem a lot because it teaches you to really understand what the meaning of each of the terms is and how to actually apply the concepts here. So, and to apply the intuitive idea as well. So here we have a regular language A, and we don't know anything about A other than it's a regular language. And so we want to look at the language A script R, which is basically all of the strings in A, but we flip the order of the symbols. So basically, we reverse every string. So if we have an example here, so let's say we have 0, 1, 0, and 1, 0, 0, for example, then A reversed is equal to, well, the string of just a single character is just going to be itself. That doesn't change because it's just one character. 1, 0 reversed is 0, 1, and the other one reversed is 0, 0, 1. And both of these are clearly regular because they have only three strings in it. And so any finite language is regular. And that's a theorem often taught in theory of computation. But we want to show that this is true for any regular language, not just a single one. So to illustrate the point, let's actually make the DFA for A. So for A, we would need to have a start state here, Q0, have a transition on 0, which goes to a state, let's call it Q1, which has to be accepting because it's accepted by A. And then we have a transition 1, 0. So let's say it goes to Q2. Then, that has to be a 0 going to Q3, which also has to be accepting. And then the 1, 0, 0 we can tack on to here, which is also accepting for Q4. And then let's make a state Q5, which is the dead state where any of the unlabeled transitions go. So let's say we have a 1 there. Everything from Q1 goes there. Q3 has a 1 going there, and Q4 has everything going there. And the common idea, if you think about it, is, well, consider the sequence of transitions that the 1, 0, 0 string takes. So it goes from Q0 to Q2 to Q3, then out to Q4. So if you think about it, well, couldn't we just reverse all of the transitions? In other words, we start in Q4 and we go backwards until we hit Q0. And that seems like a very logical idea because you're following the same set of transitions, but basically just backwards. And because you're following them in the backwards order, you get the reverse string. So I want to show why this method does not work. And to show how a right way of approaching it or modifying that idea would go. So I'm going to copy the DFA down here. And I'm going to reverse all the transitions with a different color. Let's make it red. So I'm going to make it red. So then I'm going to reverse all of the transitions here and make those a different color. So then this one's going to be the 0, 1 transition. The self loop on Q5 is going to the same state, so reversing it won't do anything. So then the 1 transition goes this way, the 1 transition goes this way, the 0 transition goes from 3 to 2, the 0 transition from 3 to 4 goes 4, 3, the everything on this transition goes the other way, and this last transition goes the other way. So if you look at this, you say, okay, well, we just start in Q4 and we go backwards. But here's the problem with this idea. Q0 is still the start state. We haven't changed that. So here, in fact, what do we say is the start state? Because even in this example, there are no transitions coming out of Q0 at all. So we can't even have Q0 being the start state because the language is empty in this case. So Q0 shouldn't be the start state in this case, but what should be the start state? Well, I think it should be one of the final states, right? Because if you think about it, if we look at the strings in A, they land in a final state. So then it makes perfect sense. If we want the strings in the reverse order, we start in a final state. But the question is, which final state? Well, for each of the three strings here, they landed in a different final state. So it's not like we can just pick one because we have to have exactly one start state. So unfortunately, there isn't a direct way that I know of to directly make an DFA. But what I can do is let's make an NFA, a non-deterministic machine. Because I don't know what the final state to start in now, but I'm going to just allow non-determinism to pick that for me. So here I'm going to make a new start state, and using an epsilon transition, I'm going to go to all of the originally final states. And I say originally final because for what we're going to see next. So here, these Q1, Q3, Q4, they should not be a final state because if we just left it like this, and if we left them final, then we can just take the epsilon transition to one of those three states, and then therefore we have accepted the empty string, but empty string is not in the original language A or the reverse language. So for that reason, these states shouldn't be final anymore. And it actually kind of makes sense why they shouldn't be, because we're looking at the strings in reverse order. So for that reason, we're going to go from the originally final states out to the start state, which is the place where we should stop. So then for that reason, the only final state in this thing is going to be the start state. So let's see that this actually does work. So for 0, we take the transition from the start state S to Q1, then out to Q0. For 1, 0, the reverse string is 0, 1. So we go to Q3, then to Q2, then to Q0 in that way. And then for 1, 0, 0, the reverse is 0, 0, 1, and we see that that's accepted too. And no other string is accepted, because if we look at every single state here, there's no way to get to any other state other than just going the backwards way. But of course, this doesn't prove it in general. This works for this example, but it doesn't work in general. So let's actually prove it in general. So let's just say that we know that A is regular, which means that A has a DFA, and let's give a name to it. So let's call it D sub A, and the 5 parameters, Q, sigma, delta, Q0F. Well, if we look at this example that we made here, we actually made an NFA, a non-deterministic machine. But we're okay with doing that because of the power set construction, which allows us to construct a DFA from an NFA. So we could go through converting this thing to a DFA, but that will defeat the purpose of the question. We only need to make an NFA here. So let's construct formally an NFA, let's call it D sub R, for the reverse machine for the language A to the R. So I'm calling the NFA D sub R, and I'm calling the language is A to the R. So let's say that the machine that I'm going to make, I'm going to call the states Q prime, sigma, the alphabet doesn't change, delta prime, Q0 prime, and F prime. So what are the 5 pieces? So we didn't delete any of the states in it, and it actually makes sense that we don't, because we want to preserve the overall structure of the DFA to start with. So we don't delete any states, but we add one state. So Q prime here is going to be the original state's Q union the, not epsilon, whoops. It's going to be S right here. So S is the new start state, where S is not in the original set of states Q. So it's a brand new state. Okay, then I'm going to leave the transition function for last. The new start state is going to be S, because that's where we're starting now. The final states, let's see, is going to be that single state, which is the original start state, which is Q0 in this case. And then the transition function is where things get interesting. So if we look at our example here, the only transitions coming out of S are empty and no character transitions. And in fact, also, there are no transitions coming out of, there are no epsilon transitions in the original, in any other transition, because the original machine was a DFA, which will make things easier. So the transition function for the new machine at state S on epsilon goes to all of the original final states. So the set of states that I can go to from S on epsilon is the original final states. And the transition function from the same state on any character at all other than epsilon is empty. I can't go anywhere on any non-epsilon transition. So here I'm going to say A is not epsilon. But then for the other transitions, so for state Q on input A, well, let's see what this is. So if we go to our picture, let's just look at the Q5 transitions that are going out on 1, for example. Well, all of the places that Q5 can go on 1 here are basically all of the states that originally went to it on input 1. And similarly for all of the other states and transitions. So here, it's actually the set of all possible states in the original set of states, such that the original transition function from that state on the same character went to Q prime. So it's all the states in the set of states, such that from there on that, hang on, it should be Q over here. Yeah, that's right. So it's all the set of states, those are the places I can go, such that originally that state Q prime went to the state Q, the state that I'm currently looking at. And then also for these, we have that Q is not S. So then for Q on epsilon is empty, because the original machine didn't have any epsilon transitions. So why does this work? So why does the language of this NFA that we made, what do we call it, dr, equal A to the R? So why does the NFA work? Well, let's see. So consider a string that was accepted by the original DFA, so W in A. And let's say that W is W1 through Wn. And look at its computation. So let's look at the states that the original DFA went on when running on W1 through Wn. So it's a sequence of states R0, R1, etc. up to Rn. And because W is in A, it must have been accepted by that DFA, so R sub n is in F. So then let's see what happens. So then look at this computation in the reverse NFA, the reverse machine. Well, it has to start at S no matter what. Well, then let's look at the reverse of all of that computation that we just looked at. So going from Rn all the way down to R0. Well, this is possible because it's an epsilon transition, so you can always do that. Well, the only way we could take Rn to Rn minus 1 means that we read Wn along the way. That's the only possible way. And then we need to read Wn minus 1, and then here we need to read W1. But that's, if we just string those together, that is the whole string reversed. Well, then we know R0 is in the final states of the modified machine, the reverse machine. So that means that the reverse of W is accepted by the reverse machine. But so then therefore, if a string is in A, then its reverse is accepted by the reverse machine. So let's look at it from the other view. So consider when W is not in A. So then let's look at its computation. So R0, R1 up to Rn, which is not in F this time, because we're supposing that it's not accepted by the original machine. Well, then let's see what happens. So let's see. So then the reverse computation must be S. So the reverse computation must be S, Rn, Rn minus 1, etc. up to R0. Actually, no, it doesn't have to be. Well, let's see. Actually, let's just understand why that's not the case. Well, Rn is not in F, right? Rn is not a final state. So then for that reason, by the construction of this machine, there's no way to get from S to Rn for that reason. So there's no possible transition for this. And then you may think, okay, this is, so then therefore it's not accepted. So that's not really true. It's because we made an NFA. And for that reason, there may be some alternate path that allows us to go from S to R0, maybe through some other final state. So just as a picture. So here's Rn, and then let's look at some other state Ri that is final. So there is an epsilon transition from S to Ri, but there's no transition to Rn here. So that's not, I probably shouldn't put a name there. There's no transition to Rn, but maybe just for example, if we do the same sequence of transitions, we eventually get to Q0, which is final. So maybe that's the case. Maybe that's true, that there's some final state that we could have went to that goes to Q0. But there's a reason that we made a DFA first. So since, what was it? D sub A was DFA, the R0 through Rn computation was unique. Right? Because for a DFA is deterministic, there's only one path from Q0 to whatever final state, whatever state it ended up in, which is Rn in this case. So if we somehow wanted to take a path to R sub I, or some other final state, well then at some point it must disagree with the computation, because if we look at like the computation that would have normally went there, so this would be Wn, and then here is Wn minus 1, etc., up to W1, and here's Q0. So basically we're just seeing what happens. So then at some point here in the middle, there must be a point at which we read Wi, and then, but then let's see. So then we have that Ri state, the supposed hypothetical final state that is gonna show that this is accepted. Well, then let's just say that for hypothesis that this actually is correct. Oops, wrong direction. So this should be Wn minus 1, and then here. Well, it can't be that it goes all the way back to Q0 with the same set of transitions, because that would contradict the fact that this is a DFA. So at some point, to agree with the original computation as much as possible, it must disagree on at least one position. So maybe it comes from this state right here that's coming from the beginning of Wi transition. So there's some point right here where there must be at least one difference in order for this to even be possible. So therefore, there is no computation that is accepting for the reverse string in the reverse NFA. And for that reason, it is not accepted. Therefore, that's exactly what we wanted to prove. So what we showed was that if we had a string that was accepted before, it must be accepted now. The reverse string must be accepted now. And if it wasn't accepted before, then the reverse string is also not accepted now. So therefore, we have shown that the language of the reverse machine, the reverse NFA, is equal to the language we want, which is the reverse one. And because NFAs, so I can write this. So because NFAs are equivalent to DFAs, then A to the R is regular. Because we just made a NFA for it, and then we can convert it to a DFA. And so therefore it must be regular. So this is what I wanted to show you, that so the technical details are not as important, but the idea of just reversing the transitions is not the right idea in terms of being complete. If you just say reverse the transitions, that's the right path to the right idea, but there are some things that you need to think about, like what are the final states? What is the start state, which is not really defined anymore? If we're going to make a new start state, how are we going to get there into the original machine, etc. So it's just thinking about, instead of just relying on your intuition, but rather thinking about the problem in a much more deep and complex way. So I hope that was interesting. If you like videos like this, let me know if there's any problem that you're stuck on, and then I can make a video for it. So thank you. Have a great day.